Okay, if we continue looking at that definition from dictionary.com, we'll see that the definition of the computer is that it accepts data, performs operations, and displays results. There's actually something missing from that, though, and that is that it doesn't include the instructions that control how all of that happens. And those instructions are called the software or programs that the computer runs. Broadly divided, we can classify software into two types: system software and application software. As far as this class goes, software is where it's at because that's what we're interested in creating is software. So, computer software. In terms of system software, what that is the operating system. That's what directly manages the hardware of the computer. It presents a user interface to the person using the computer. So the operating system is what creates the windows and the buttons and the list boxes and things like that that you can use to interact with the system. And there are both commercial and open source options. So for instance, you may have a computer that runs Windows or a computer that runs Mac OS X, or you may have an open source option like Linux. The other classification of software is application software. And those are the software tools we use to do work or to have fun. So those are the things that we use on the computer that actually get something done. So some examples: Microsoft Office, Photoshop, game software, your MP3 player, iTunes, etc., etc. All of those are application programs. And there are also open source and commercial options for software. So for instance, there's Microsoft Office, which is a commercial solution that you have to pay for. Or there's OpenOffice, which does similar tasks but can be downloaded legally for free. And nowadays there's almost always an open source alternative for just about anything that you want to do. Okay? Well, application software is what we're all about. In this class, we're writing our own application software. So we're creating our own apps for the computer using the processing programming language. Okay? Now, we need to talk about data representation. All that information inside the computer, all the data and the programs, that has to be represented by some set of symbols. So, just like our thoughts, ideas, and concepts are recorded using the symbols or letters of our language, English, similarly, a computer has to do the same thing. Okay? Computers use a binary system, though, where they have only two symbols, zeros and ones. So in English, we have 26 letters, we have all of our punctuation, we have space, we have the digits, and we use all of those pieces to set down our thoughts. But computers have to do all of that using only zeros and ones, patterns of zeros and ones. Okay? Everything that's stored or processed by a computer is represented by those patterns. So every program ultimately is a pattern of zeros and ones. Every MP3 file that you have, every game that you play, every video that you watch, ultimately is represented by some really, really long pattern of zeros and ones. Now we're going to focus just on one simple case. We're going to look at numbers, how those are represented in binary or a 2-bit system. Okay? So for reference, let's use what we normally think of for numbers. We represent numbers using base 10 or a decimal system and the so-called Arabic numerals. So we have 10 symbols, 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. And obviously other things convention-wise like commas or decimal points or sign symbols, but generally speaking, just the numerals are what we use. And we have a place value system that lets us convert in our head those numerals that we read into an actual value. Okay? So every place in a numeral represents a power of 10, and that's how we can tell what value the representation has. So let's take a look at an example. Here's a number 537. Okay, well, 537, each place in this number, or this numeral rather, represents a power of 10. So starting from the right-hand side and moving left, this is our ones place, or 10 to the 0 place, tens place, or 10 to the first place, and our hundreds place, or 10 to the second place. Okay, so 10 to the 0, 10 to the first, 10 squared. So 537, if we expand it out, is 5 times 10 squared, because that's in the 10 squared place, plus 3 times 10 to the first, because 3 is in the 10 to the first place, plus 7 times 10 to the 0, because 7 is in the ones place. Doing the math, 5 times 100, plus 3 times 10, plus 7 times 1, or 537. Well, it works just the same in binary for numbers, except we're using base 2. So we only have our two symbols, again, 0 and 1, and now every place in the numeral represents some power of 2 instead of a power of 10. Okay, so for example, here is a binary numeral, okay, a number represented in binary representation. The subscript 2 here just tells us that it's binary and not decimal. So this rightmost place represents 2 to the 0, 2 to the first, 2 squared, 2 cubed, 2 to the fourth, and 2 to the fifth. So if we expand that out, we have 1 times 2 to the fifth, plus 0 times 2 to the fourth, plus 1 times 2 cubed, plus 1 times 2 squared, plus 1 times 2 to the first, plus 0 times 2 to the 0. Okay? Just the same as the decimal, except that our places and our powers are different, or our base rather is different. So now we can do the math. 1 times 32 plus 1 times 8 plus 1 times 4 plus 1 times 2. Add all those together and you end up with 46. And so that shows us how to convert from this binary representation here into a decimal representation. Okay? Now, we also have the idea of hexadecimal representation, otherwise known as hex, and that uses base 16. And that's really just a way to shorthand large binary numbers to make them shorter and easier to read for us. So in hex, we have 16 symbols, 0 through 9, and then A, B, C, D, E, and F. Okay? Every place in a hex number represents a power of 16 instead of 10 or 2. But other than that, everything works out just the same. So the upshot of this is that every hex digit, if you will, stands in for 4 bits. And so, like I said, hex is a handy shorthand for large binary values. Let's take a look at an example. Here's a number in hex, 6FE8. In base 16. Again, the subscript just tells us what base we're in. So this is the 16 to the 0 power, 16 to the first, 16 squared, 16 cubed place. Okay. So we've got 6 times 16 cubed, F times 16 squared, E times 16 to the first, and 8 times 16 to the 0. Well, we have to figure out what F and E mean. Turns out that F in decimal is 15, E is 14. So if 6 times 40, 96, plus 15 times 256, plus 14 times 16, plus 8 times 1. Add that all up, and we see that 6FE8 in hex is 28,648 in decimal. Okay? Now, for more detail and other examples of converting between these bases, you can take a look at some other videos. We've got a byte about data representation, so you can look at that. Obviously, you can also read the text and figure out how those other conversions work.